Hi everyone, so in this video we are going to be talking about how to formally compare partially ordered sets. So we've seen previously how to draw partially ordered sets, and there's these very nice diagrams which faithfully capture all of the information of the partially ordered set, and these are called Hasse diagrams. And just to give you a few examples, you can see here on the screen in the top row, this is the partially ordered set of the set of all subsets of a given set. So for instance, all the way to the right, this is the set of all subsets of the set X, Y, Z ordered by inclusion. And at the very bottom right, you'll see the set of all divisors of the integer 30 and ordered by divisibility. But the question we want to take a look at in this video is, why do these partially ordered sets look so similar? And in fact, this is just going to be an example of a general concept. The real question that we want to ask ourselves is, how do we formally compare partially ordered sets? Okay, so let's answer that question immediately and get to a definition. So here is the main concept behind translating one partially ordered set into another. This is called an order-preserving map. So a map F from a partially ordered set P to a partially ordered set Q is called order-preserving if it satisfies this implication here. So that is, if in P I take two elements that are related, that is X is less than Y, then when I map them across, that order relation should be preserved, and that's why it's called order preserving. So of course not all maps will satisfy the condition. I mean, just to give you a really bad example, here is this partially ordered set and here's this one, the same one. Now if we just consider the map which takes 1 to 0 and let's say 0 to 1, then the relation is not preserved, okay? Because 0 is of course less than 1, but when I map it across, I'm not going to get that 1 is less than 0. And so the order is not going to be preserved. So just to be clear, what I have is I have that 0 is less than 1, but I do not have that when I map across, if this was f, that f of 0 is less than 1, f of 1, sorry. So because I don't have this, this map is not order preserving. All right, so let's just go back to the these partial ordered sets that we saw at the beginning of the video. Here they are. So our job is going to be to construct maps, order-preserving maps, going from here to here. I think that's going to be quite obvious. There's only one. Also from here to here, and from here to here, and also from here to here. And these are going to have to be order-preserving. But in fact, what we're going to do is a little bit more than that, because we're going to construct these maps going in one direction, but we're also going to construct maps going in the opposite direction. And just to be a bit intuitive here, what are these maps really doing? Well, they're relabeling the Hasse diagrams, really. So when we can consistently relabel one Hasse diagram into another and backwards, we have a special concept to deal with this. So when Hasse diagrams really do look the same as they do here, there's a special concept for capturing the situation, and this is what's called isomorphism. So let me explain what is an isomorphism. Here we are. So given a partially ordered set P and a partially ordered set Q, this concept here of isomorphism is formally capturing that we can consistently relabel one Hasse diagram, or the Hasse diagram of P into the Hasse diagram of Q. Just in other words, that P and Q effectively have the same Hasse diagrams up to a relabeling. Okay, so what is the concept? The concept is that P, the partially ordered set P, is going to be isomorphic to the partially ordered set Q if we can find two maps, namely one going from P to Q, that's the F here, and then another one going from Q to P, let's say G, and they have to satisfy these inequalities. Sorry, not inequalities, equalities. And what do these equalities guarantee? Just that our relabelings are in one-to-one correspondence with each other. So, in other words, going from P to Q and then going from Q back to P is going to be have 0. It's going to do exactly nothing. So all of the information is taken from P to Q. There's no information loss. It's another sort of intuitive way of seeing what this concept does. But in any case, these are all formal. So let's try and be a bit more formal here, and let's talk about this partially ordered set of divisors. Okay, so just to jump across here, we're going to talk about divisors and power sets. But before doing that, I want to go back to the first, the very first minute of the video, where we saw the partially ordered sets given by the subsets of x, y, z. But instead of x, y, z, let's talk about the subsets of 2, 3, 5. Now, when we look at the subsets here, it's because we are dealing with a 3-element set, we're going to get the same diagram as the subsets of x, y, z. But the relationship of this diagram to the diagram here is going to be a lot clearer, I think. Because, well, 2 is going to go to 2, and 3 is going to, of course, go to 3, and the singleton 5 is also going to go to 5. But how could we get, what is the sort of general way of taking this subset to 3 to 6? And however I describe that process, it should be the same as taking the subset 2, 5 to 10 and 3, 5 to 15. Well, I'm sure you can see what it is. We're simply multiplying all of the elements together in the set. And that method is going to work for the blue box here, and also, of course, the yellow box, and so on. And also, of course, this top element here, 2, 3, 5, gets mapped to 3, because if we multiply all of the numbers 2, 3, 5 together, we're going to get 30. All right, so we have a candidate here for going from one diagram to another. We're going to just simply multiply all of the numbers in the set. So from this set here, so at the top here, each of my elements are sets of numbers, and the way I'm going to map to the partially ordered set of divisors of 30 is just multiply these divisors together. Okay, so let's try to be a bit more formal here. So what I've just described is a general thing, and that's just given here. So firstly, just to be clear, the partially ordered set that we were looking at earlier, the divisors of 30, just to say how it is formally defined, well, here it is. It is really just given set theoretically like this. So we take all the divisors of an integer n in general, where we're not just talking about 30 now, but n is any integer, any positive integer bigger than 1. And then what we're going to look at is the prime divisors of our integer n. And this is just going to be a set. So here we're looking at a set of integers, namely all divisors of our integer n, and here we're looking at a subset of that one. So we have that this is a subset, and this is just the set of all prime divisors of n. And to just give you an example here, the prime divisors of 30 is just given here, and all divisors of 30 are just given by the integers you can find in the circles here. Okay, so we have these two notions here, and now we can form an isomorphism between, well, not yet an isomorphism, but just to describe the process for 30, we can describe an isomorphism here. So if I give you a divisor d of n, what I'm going to do is send that divisor to p div of d. And what is this object here? Well, it's a set. It is a set of prime numbers which divide d. And for that reason, it's also going to be a set of prime numbers which divide n. And so for that reason, it's going to be a subset of, it's going to be an element of the set of all subsets of the prime divisors of the integer n. Okay, good. So we have a map which is given by simply this pdiv, which goes from the divisors of n into the subset, all subsets of prime divisors of n. And we also have a map going in the opposite direction. We're going to take given a subset of prime divisors of n. So we take a subset here, S of p div of n. How we're going to go back to a divisor of n is we're just going to take the product of all integers that you find in the subset S, and that's just given by this formula here. So the claim here is that for the integer n, this is going to be an isomorphism. And that's quite nice. So you can actually see that isomorphism explicitly. Let's just go back to our picture again we saw earlier. Okay, here it is. So here's the picture we were looking at earlier. So at the top you'll see exactly, this is exactly all subsets of pdiv 30. And here we have exactly div 30. Okay. And those two maps we described earlier do exactly what we expect them to do. Firstly, the map going from here to there, which we said was just the product map. It will take 2, 5 to 10, and so on. And then to go backwards, we take our integer, and then we look at all of the prime numbers which divide it. And so you'll see that this goes back to 2, 3 here. And so we have what we've produced here is two maps, one going from the subsets of all prime divisors of 30 into the divisors of 30, and then backwards from all divisors of 30 into the subsets of all prime divisors of 30. Okay, so what we've done here is produced an isomorphism, a partially ordered set isomorphism between two different objects. And let me end this video by asking you a question. So the question here is, for what integers? For which integers? So let me actually write this down as a question for you to answer, and then let's see what we can come up with. So the question is, for which n, let's say bigger than 1, is this map, are these two maps an isomorphism, a pair of isomorphisms? So let's just say an isomorphism. So that's the main question that I want to end this video with, and then we can revisit this question in what follows. So of course, there's a general story here. Let me just show you that not all integers, so just to show you an example, not all, there are integers n for which this will not necessarily be an isomorphism. So for instance, let's look at div 12. Okay, so div 12. Well, what is this? Well, we're going to have a few divisors here. We're going to have 1, of course. We're going to have 2. Then we're also going to have 3. We're also going to have 4. We're also going to have 6, and then 12. Okay. So here you can see these are all divisors. If you want to just see the diagram, we might as well draw it here. Here's 1. Here's 2, and then 3, and then we can also go one step further in the direction of 2. We can go to 4 here. And then here will be 6, and then here will be 12. Okay. So these give you this shows you the Hasse diagram. And the thing to see immediately is that this is not going to be these two maps given up here are not going to be isomorphisms. So if we look at what is pdiv, okay, pdiv is going to be so pdiv of 12, sorry. This is just going to be all the prime divisors of 12. And if you look at that, well, there's only two prime numbers here. It's 2 and 3. So this is just 2 and 3. So if we look at sub of pdiv in this case, this is going to have 4 elements. So let me just say that. It's going to be 4 elements here. Whereas on the left-hand side, we're going to have 6. So of course, this can't be an isomorphism up here. And so the question is an interesting one. So the question is, for which integers n bigger than 1 do we get an isomorphism? Okay, so let me leave you with that, and I'll see you next time.